So the integral test does a great job at determining a lot of different series, whether they converge or diverge. But it certainly has some drawbacks because number one, the function that you're working with has to be integrable, and not all functions are. In fact, there's really only a fairly small subset that we can work with. So that's not ideal. And secondly, going through the process of integration can be involved. It could require just U substitution, or maybe trig substitution, or some other advanced techniques that just take a while to actually work through. So it would be nice to have some more methods that we could use that were A, easier and faster to apply, and B, worked for more types of series. So that's where the comparison tests will come into play. And it kind of fills both of those requirements. There's two different comparison tests. The first that we'll talk about here is the direct comparison test, and then in a little bit we'll discuss the limit comparison test. So the direct comparison test, what it does is it just simply says, if you can find a similar series, whether that if it converges or diverges, and generally you're going to get one from like a P series or the geometric series, because it's easy to come up with a series and know whether it converges or diverges. And when you know if it's converging or diverging, you can compare each of those elements to the elements in the series that you're currently interested in. And let's say the original series is convergent, and all of the elements in the series you're interested in happen to be smaller than that. Well, then you would know that this series would converge as well. So for instance, it maybe looks like this. So we have, say, A sub n, which is a known series. And we create it with a P series or a geometric series, one of those two generally. And let's say it converges. And then we have B sub n. So it's just another series, but we don't know what happens. All right, now, A sub n, all of those terms of the sequence go to 0, and I'm drawing this as a curve. Of course, it would be just points, but I'm drawing the elements as a curve. Now, if B sub n, if all of those elements happen to be smaller, well, if A sub n is going to 0 fast enough to converge, then B sub n would be going fast enough to converge. So B sub n would converge if all the elements of B sub n are less than or equal to all the elements of A sub n. Now, what happens if B sub n happens to be larger? Well, we can't really draw any conclusions, because if A sub n converges but B sub n is larger than that, it doesn't really tell us if B sub n is going to 0 fast enough to converge. So this is the only way it works here. And then the reverse of that, I'll draw out here as well. So let's say we have A sub n, which is a known series that diverges. All right, so it's going to 0, but it's not going to 0 fast enough to converge. So A sub n diverges. And again, we've created it from something simple like a P series or a geometric series. And then we just compare element by element to B sub n. All right, so B sub n is the one we're interested in. And if all the elements in B sub n are larger than all the elements in A sub n, then b sub n would also diverge. So if b sub n is greater than or equal to a sub n. If b sub n happened to be less than these elements, well, again, we wouldn't be able to draw any conclusions because that b sub n might be going fast enough to actually converge. We don't really know. So you have to be very careful in this comparison test. It's really strikingly straightforward, but you have to be careful and make sure you don't draw conclusions that you're unable to draw. Now, the formal statement of the direct comparison test is written here for you, but to be honest, this is how I go about doing the comparison test. Is I just tend to draw little sketches off to the side and remind myself, all right, so if I have the known series, are the elements of the unknown series larger or smaller, and would that tell me if it can converge or diverge? So let me walk you through some examples and show you what I mean here. So the first example says to use the comparison test to determine whether the series converges or diverges. And that actually should say the direct comparison test. So let's look at this first example. For the following series, use the comparison test to determine whether the series converges or diverges. And I guess technically that probably should say the direct comparison test because there's more than one, but that's all right. So here's what we would do. So it doesn't really matter if we call this the original series a sub n or b sub n. Let's say this is a sub n. Okay, and that is what we want to determine if it converges or not. So I'm going to use the direct comparison test, and I'll just label it like that. So the direct comparison test, what we need is something to compare to. So we're going to compare this to, I'm going to pick a p-series because it's fairly similar to a p-series. If it was just 1 over n cubed, that would be perfect. But it's got n cubed plus 3n plus 1. But I think the most logical thing would be to compare it to the p-series, where n goes from 1 to infinity of 1 over n cubed. So that's a p-series with p equals 3, and that's greater than 1, so it converges. And this is all stuff that you need to write down to make a complete test here. So you need to state what you're comparing to and what happens with it. All right, so now that we have a convergent series, we need to show that a sub n, I'll go off to the side, because like I said, this is something I always do. So we have the known series. All right, and I'll call this b sub n. And it converges. So what we need with a sub n is a sub n would need to be going to 0 faster. So all of its elements would have to be less than or equal to b sub n. All right, so the test here basically is to show that. So we need to show all the elements of a sub n are less than or equal to b sub n. Now, it's really easy to mix up the order of that inequality, which is why I literally just draw this diagram every single time, because it makes it fairly trivial to get that correct. So the elements of a sub n would look like 1 over n cubed plus 3n plus 1. We need that to all be less than or equal to the elements of 1 over n cubed. Now, when you're working with inequalities, you do have a little bit more freedom than working with strict equalities, but basically the process is the same as working with solving an equation. One thing you do need to be careful of is if you multiply both sides or divide both sides of an inequality by a negative, then it reverses the order of reverses the direction of the inequality symbol. But what's nice is everything's on a positive domain, so we wouldn't have any negative numbers with either of these, so we don't really have to worry about that. We can freely work with both sides of the equation through multiplication and division and not worry about reversing the sign of the inequality. Now, when you have two fractions in an equation or inequality like this, one thing you could do is cross multiply. So if I do that, I would end up with n cubed times 1 would be n cubed. N cubed plus 3n plus 1 times 1 would be itself. And then I could subtract n cubed from both sides, and it would cancel that term on each side. And I'm left with 0 is less than or equal to 3n plus 1. Now, this statement right here, for when n is greater than or equal to 1, 3 times a positive number plus another positive number is always going to be bigger than 0. So at this point, you can be certain that this inequality holds. I will advise to not state that your inequality holds too early. All right, because the thing is, like, just starting here, you know, it might seem obvious enough to you that that does actually work, but I want you to work this inequality out till it's obvious enough to like a third grader that it's going to work, okay? So you need to take the inequality down to the point where, like, it's just absolutely no question that the inequality holds, okay? So, because honestly, sometimes you might be surprised that it doesn't actually hold. You just have to kind of work through a little bit. So this works, that checks out, and therefore, since the inequality holds, a sub n would also converge. So a sub n converges by the direct comparison test. And that's what a complete test looks like. You need to state what you're comparing to and what happens with it, and then perform this inequality to make sure that it all works. Let's try some more. All right, the second one, for the following series, use the direct comparison test to determine whether the series converges or diverges. Now this time, this is really similar to a geometric series, but it's not a geometric series. It's only off by an additive, like +1 here. That's enough to make it not a geometric series. So you can't just say that it converges as a geometric series. You'd have to prove it through some other means. Now, that other means is going to be the direct comparison test. And we're going to compare this to the series n equals 1 to infinity of one half to the n, and I'm going to call this series b sub n. Now, nuance time. Okay, so yes, my geometric series is starting at 1. This exponent is supposed to be n minus 1. However, we could make that happen, but we would also have to make an equivalent change over here as well, okay? But the thing is about the direct comparison test is this little statement right here says that you can ignore the first finite number of values anyway. As long as the last infinite number of terms works, you can ignore the first so many. So we're basically going to use that so we can ignore the first term and therefore just prove that the rest of them work. It will be fine. So that's not a problem here. If we were trying to find the sum of this geometric series, okay, we need to take that into account. But if we just want to know if it converges or diverges, that first term isn't going to make a difference as to whether it converges or diverges. That's the idea. All right, so I'm going to do this, and this is a geometric series. And r, in this case, is equal to 1/2, which is less than 1, so therefore it converges. All right, great, so we know it converges. So over here to the side, here's, tell you what, a sub n, and I'll put b sub n in a lighter color. So b sub n converges. All right, so a sub n, what we want is for it to be entirely less than in order for it to converge as well. All right, so the test here is to find that out. So is a sub n less than or equal to b sub n? So a sub n is 1 over 2 to the n plus 1. B sub n is going to be 1 over 2 to the n. And then just went ahead and raised the fraction itself to the nth power. So 1 to the n is just 1, and then over 2 to the n. All right, all of these terms are positive. We can cross multiply, that's great. And then if we subtract off 2 to the n, those terms cancel, and this is about the nicest result you could possibly get. 0 is definitely less than 1. All right, so that's a true statement. So that checks out. So therefore, they both converge. So a sub n converges by the direct comparison test. And just as a matter of, understanding, like when you do your homework, generally you identify the type of test that you're working and whether it converges or diverges. On your paper for your test, you need to have everything that I've written here. All right, there's not much less that you could write to make this a complete test. So you need to state what test you're using, what its setup is, the actual test itself, and the result. So just make sure all of that's on your paper when you turn in your exam for backing up your work online. Okay, here's another one. N equals 2 to infinity of 1 over the natural log of n. And the reason this is starting with 2, if we use the natural log of 1, that's going to be 0. So it's going to be 1 over 0. So that's an undefined value. So we've started at 2 instead. But that's all right. We need something to compare this to. 1 over the natural log of n, this sequence certainly would go to 0 because the denominator is changing, but not the numerator. So that holds. But what exactly do we compare to? Well, for the most part, all we really can use for direct comparison is tests that we already know. All right, so like for instance, I could compare this to, let's say, the harmonic series. So 1 over n. It doesn't exactly look just like what I have here because there's no logarithm, but logarithms grow very slowly. So I have the idea that this is probably not going to 0 fast enough to converge. So I'm picking a series that looks similar, but also diverges. So this is the harmonic series, and therefore it diverges. So what we would need, right, so we'll call this B sub n, and it diverges. So then A sub n, we would need it to be going to 0 slower than that. So A sub n would need to be larger than the values of B sub n. Okay, so let's test and find out. So we want A sub n to be greater than or equal to B sub n. And you really don't need this diagram if you remember correctly what the order of this inequality is going to be. But I tend to just use the diagram because it helps prevent making a small error that would throw the entire test off. So A sub n is 1 over the natural log of n. We need that to be entirely larger than 1 over n. Okay, again, all these terms are positive, so we can cross multiply. So n is greater than or equal to the natural log of n. And you do need to get this to a point where it is understandable by, like a third grader, for instance, and that the inequality holds. So this for you might actually work out because if you think about the graphs of like the natural log and n, all right, so n does grow faster than the natural log of n. But not everybody really has an intuition as to what happens with logarithms. So another thing you could do is like raise both sides of this equation and make it an exponent with base e. So then you would have e to the n is greater than or equal to n. And it might actually be a little bit easier to comprehend that an exponential function is certainly growing faster than a linear. So this holds, that's true. Third grader might not believe it, but it's fine. So an exponential is definitely going to grow faster than a linear. That's sufficient. So A sub n then would do the same thing that B sub n does. So it diverges by the direct comparison test. Okay, another one here. And in this example, it says that sometimes it can be difficult to find an appropriate series for the direct comparison test. And so we have this one, which looks innocent enough, but let's see what happens. So if we do the direct comparison test, I think the most obvious thing to compare to would be a p-series of 1 over n squared. So that's a p-series with p is equal to 2, which is greater than 1, so it converges. Okay, so we're expecting convergence. And let's say this is a sub n. I think I've been inverting my collars the whole time, but that's okay. And actually, I probably should have put b sub n on there first. So let me do that. So that's b sub n. All right, b sub n is going to 0 fast enough to converge, so I need a sub n to be entirely less than b sub n. Okay, so that's my test to prove that a sub n is less than or equal to b sub n. Now everything seems like it's going to work out just fine. Let's see what happens. So 1 over n squared minus 1 less than or equal to 1 over n squared. Now it's n squared minus 1, but when n is equal to 1, we would have 1 over 0, which is fine. We're not actually comparing at n equals 1. We started at 2. So starting at 2, that would be 4 minus 1 in the denominator, which would be 3. And every term after that's going to be positive. So we can cross multiply, not worry about any changes to the inequality symbol. Then subtract n squared from both sides. That's great. That thing cancels off. And then we have 0 is less than -1. Wait, what? That's not true. All right, everything looked like it was going to work out just fine, but this isn't a true statement. 0 is bigger than -1. So this is false. So what that means is the direct comparison test fails. If that inequality doesn't hold up, then you haven't proven anything with the direct comparison test. Even in an example like this, where it looks like it should be relatively obvious, it just doesn't work. But that's all right. We have another type of test, which we will talk about in the next video, and hopefully shed a little bit more light on this particular example.